is Bintang Yuwono, and he will present a paper, a very interesting paper about energy system modeling for regional power sectors in the deep decarbonization. So if it's okay, Bintang, the floor is yours.
Okay, yeah, thank you, Arthur, for the introduction. Hello, everyone. Thank you for the opportunity for me to, wait, I have to share the screen first. Okay. Okay, yeah. Hello, everyone. Thank you for the opportunity for me to present my topic for my research here on the modeling aspects and challenges in energy system modeling for regional power sector deep decarbonization. So the outline of this presentation will be carried on as follows. Start with the background about the energy system modeling and in the scenarios of a deep decarbonization, and the methodology of this research on conducting this review of different aspects and challenges regarding energy system modeling, and presented the results of this research about the key aspects and challenges, and followed and ended up with the conclusion side. So to introduce the issue here is that deep decarbonization of the power sector plays a key role in reducing total greenhouse gas emissions dramatically to meet the climate stabilization goals. And the common strategy is to avoid, to reduce, or to remove carbon emissions from electricity generation and use those low carbon or carbon-free electricity to help decarbonize residual emissions from other hard-to-reduce sectors such as transportation, building, industry. So charting a path towards power sector deep decarbonization is a complex task, considering the wide-ranging portfolio of technological solutions and respective challenges. A good fit model is suitable for scenario analysis to help substantiate questions related to system capacity deployment and operation, as well as to provide insights on how the system behaves in a given condition. So the research question here is, in assessing pathways of regional power sector deep decarbonization, what are the aspects of energy system modeling that need to be considered? What are the challenges in modeling the complex electricity supply chain, and how to address these aspects and overcome those challenges? So as we know, the key issues related to the energy system, that power sectors deep decarbonization need to integrate large-scale renewable energy resources and carbon capture, transport, and storage technology. There are risks of over or underestimating potentials and impacts for not considering the spatial and temporal implications. This is mostly regarded to the access, quality, and cost of different energy sources, and also carbon, we call it as source and sink matchings. And also, in addition, there's protection and conservation values that implicates towards the resource and infrastructure deployment for the energy system. So in summary, the spatial temporal implication of the energy system and infrastructure deployment are critical in influencing the cost and configuration of expanding the electricity supply chain, especially in the case of connecting large untapped population and the integration of wide area renewable energy sources and CCS technologies. Yeah, so the aim of this review is to give a comprehensive overview and to discuss the key aspects and challenges of special explicit energy system modeling for regional power sector deep decarbonization. There are different focuses of different literatures that I classified here to give an insight about the aspects and challenges. First is that those that focuses on the grid-based multi-energy system concepts and modelings, where there are different energy processes and networks to be considered in a full energy system or an energy supply chain. And then there's the biomass supply chain model, different supply chain analysis for the biomass feedstock in a process. And there's the generation and transmission co-optimization model, where this considers also the transmission and distribution on top of the generation problem. And there's the carbon capture and storage infrastructure model that considers different networks of CO2 capture and storages for the energy sector. And there's the integrated assessment of energy system externalities, and there's the evaluation of energy system modeling frameworks. So we start with the finding when we see the aspect of modeling is especially in the scope and coverage that it tried to address the real problem. So the decarbonization of power sector is achievable through deployment and operation of low, zero, negative carbon electricity supply technologies. And the power sector capacity planning aims to secure an adequate, reliable, and cost-effective electricity supplies to the region. So this have a correlation in how decision on investment, such as size, the sitting, and when the technology can be deployed, or the operation of such technology to produce or to supply electricity became the question on how the decarbonization of the power sector can be achieved. So the scope, it will be about a long-term capacity investment planning, but with considering the short-term dynamics related to operating activities. It covers, when we say regional, it covers a region that consists of a country or multiple neighboring countries, such as the European region or the United States, for example, that have different states. And this comprises of different sub-regions that are then became interconnected with different transport corridors to transfer energies between locations. And the time horizon for deep decarbonization in this context, the time horizon must cover up to the end of 21st century at least. This in line with the targets of the Paris Agreement. That it also include the net zero target by early second half of the century. So envisioning this kind of pathways requires an understanding of how the energy system could evolve in the future with scenario modeling. So the system boundaries that we consider must be carefully defined in order to comprehensively assess the various deep decarbonization strategies, especially when we categorize those strategies as in three ways, using low or zero or negative carbon technologies by means of using different kind of energy carriers that have different how we call it, emissions impacts, such as using lower emissions natural gas and biomass to exchange high emitting oil and coal, and also to use zero carbon technologies here by means of the zero carbon in point generation, which is using renewables energies. And also the negative carbon technologies when we envision the use of CCS, the coupling with biomass to create carbon dioxide removal, or using direct air carbon capture and storage. And all of these will impact how the electricity that is supplied to fulfill the demand in the region. So the case here would be the electricity transmission and distribution network, where electrification there are many different electrification options and challenges that accompany them, such as the choices to extend existing grid or to create a mini grid network that are kind of isolated from the main grid, and also to choose whether to make a standalone system where in remote areas usually. And also the challenges in deep decarbonization is to integrate large-scale renewable energy sources. The characteristic of renewable energy sources, starting from the variability, it can create the profile cost here, because there's the risk of inappropriate load matching, where there are risks such as undergeneration or overgeneration during the different load of those renewable energy sources, and also the load of the demands. There's also the characteristic that it is uncertain, because day-ahead forecast errors can be happening for renewable intermittent renewable generation. and also the location specificity of renewable energy. It requires large transmission to transfer high supply renewable energy regions to demand centers that are lacking of these potentials. There's also the case when we consider a biomass coupling into the energy system, the cost of biomass and use fossil and fuel feedstock for electricity generation are largely influenced by how those resources are procured, treated, and transported. And for example, countries with large biomass potential that coming out to export mostly, and how they consider it to be used domestically in a competitive way, they require to understand the improved supply chain for the domestic measures, such as how they collect, they refine, they transport and store, or to feedstock for power generation facilities. There's also different carbon capture, storage, and also utilization technologies that can be coupled to the energy system to actually achieve that vision of a negative carbon electricity in a deep decarbonization scenario. So there are different capture points or technologies that are considered. There's also the network to transfer these captured CO2 to point utilization or storage. And the protection and conservation values implies to the energy sector development, implication to the energy sector development in terms of their resource usage limitations, their sitting suitability, disregarding the infrastructure deployment, whether those land are protected, restricted, or sort of, and the operation of energy system, the energy technologies, disregarding to the emissions or pollution controls and different renewable feed-in tariffs that actually make the operations kind of more feasible to or competitive to the existing market. So with those challenges for deep decarbonization, this comes into the cost for modeling effort in terms of increasing those level of complexity, where it should represent the physical flows of energy along the electricity supply chain, and also the CO2 when we have CCS enabled there. So there are different level of complexities that need to be considered when we have different components of the electricity supply chain in the context of deep decarbonization. For example, when we have electricity generation problem combined with electricity transmission problem, combined with the CCS infrastructure problem, this became a really complex problem if we consider each aspect in the same way as a complex electricity system, for example, with different part load efficiency or the AC/DC conversion that made it more complex. But then there are choices there to actually use assumptions to make the model more simpler, such as a black box approach that uses constant efficiency instead of sort of part load efficiencies. So this consideration becomes to make it more complex or more simple for the model. And the aspect of the spatio-temporal resolution is important because in this electricity supply chain in the region, we know that the energy is not always supplied where and when it is required. This imbalance may be complemented through transmission grid. This is to reduce the spatial problem between energy supply and demand, or held by storage to discharge at later time. And this is to solve it temporarily by holding it, charging it, and then charging out in a different time. So this issue about spatial consideration became important when we consider the different fuel costs, the different access quality and costs of different energy sources in different regions. So, for example, when we define the complexity of the different components, it can be mapped in different level of spatial and temporal resolution. For example, here, if we consider the electricity transmission and the generation and storage at the same time, it has to have a same level of detail to consider the movement of electricity and the supply and demand in a timely manner. That requires much more compared to fuel feedstock and CO2 transport, because they can be temporarily stored as means as it's not so hard like electricity. So the consideration can come down to an annual basis instead of like hourly basis for electricity. So in terms of the model formulation, there are two types, the two groups, depending on how they approach to the problem. It can be a simulation or an optimization or a backcasting. This is to provide scenario of how the energy system should evolve given a future state compared to the optimization part. And there's the partial equilibrium model, there's the agent-based model that consider the system as agents that individually assess its own situation and makes decision based on a set of rules. But also there's regarding how they address the uncertainty of the problem, is about using a deterministic understanding model or a stochastic or probabilistic model. This uses deterministic, using different assumption and data that consider the best estimates, while stochastic modeling uses the probability distribution of data and assumptions to allow this random variation in one or more inputs over time. This approach actually make the model much more complex using the probabilistic distribution. And there's also the aspect of data, where finer spatial and temporal resolutions of the model requires appropriate values of both the dependent and independent variables. In this vast amount of data required is often not available because it is not measured or commercially confidential, or it's highly uncertain or in bad quality. So, or it's also available in different spatial temporal resolutions. So the data can be coarser in those resolution, or it can be finer. But then there are also approach on how to make the required data in the same level of resolution that the model required through downscaling or aggregation of data.
Bintang, sorry to interrupt. 2 minutes left. It's okay. 2 or 3 minutes left.
Okay, I'll be short in this part. So there's also the aspect of assessment criteria. We consider different dimensions here. There's the technical dimension, the techno-economic dimension, the socio-technical, resource, and environment. So the climate change mitigation and the sustainable development goals provide the integrating framework for assessing the feasibility of energy technology options, with considering the integrated multi-dimension interaction between those technology, resources, society, and environment. So these will be considered for choosing different energy technology options to consider whether it is affordable, secure, accessible, acceptable, and sustainable. So there are the challenges here, especially in addressing space and time. So selection of spatial temporal resolutions should consider the extremes where decisions may shift. For example, if we decide on expanding a transmission line, usually the cost information is per kilometer costs or per 10 kilometer costs. Then to what extent those information can be inputted to the model and to consider how we should consider how resolution is defined. It became a challenge. So the approach is to make a spatial clustering of these different demand, resources, plant sitting in a different locations to aggregate it in one location. This clustering method reduces the amount of variables that needed to be inputted into the model. And also regarding this, the appropriate assumptions and methodology are critical in delivering comprehensive results, thus minimizing the required computational resources. So the issue about scale and complexity, we approach this through problem simplification or decomposition of the problem to make the model more tractable, or which is easy to deal with. And the third challenge here is the multi-dimension feasibility assessment. So coupling or linking technology-rich bottom-up models with economy-wide top-down models can integrate this large set of externalities to be considered without significantly increase the computation resource requirements. So such as coupling this energy system model bottom-up technology options with CGE or partial equilibrium kind of model to assess these different aspects external to the energy system. There's also the challenge in uncertainty, transparency, and reproducibility.
One minute left.
Okay, so thank you. Regarding the availability of data, as we discussed before, that the required data can be downscaled or aggregated from different spatial temporal resolution if it's not available. But those data can also be information that are determined with best estimates or expert judgments, or with probability distribution around the data, such as wind resource distribution. These need to be addressed, the uncertainties there, whether using determined data or probable data, using different approaches there. That is to improve, that will require, but in the process to address these uncertainties, there also need to be improved in the aspect of transparency to ensure that the process there can be evaluated on how they address the uncertainties. So improving the transparency and responsibility, the concept of open source modeling, provide an open data for the data processing part, but also provide an open access for the model formulation and choice of software. There's also the open data in terms of the results and how the results is processed. So in conclusion, this paper provides an overview of the current research and challenges of the modeling of the energy system for power sector deep decarbonization. The key modeling aspects and challenges that need to be considered in the model development have been discussed there. So there are the aspects there about a robust and efficient analysis of the power system in the context of deep decarbonization. There's also the aspect to incorporate the complex interaction between various energy carriers, processes, networks, focusing on electricity generation, storage, distribution system, and power flows. There's also the long-term capacity planning model that should account for securing supply system in the short run. There's also the model formulation, and data need to be adjusted to be best substantiate the problem in question. So the challenges there can be sort of addressed with coupling short-term operation model with long-term capacity planning. There's to increase model complexity, also to account for externalities that will hamper model tractability, and also to soft link bottom-up and top-down model option solution there. And there's also the aspect of open data, open source, and open access that need to be addressed to increase transparency and furthermore increase the modeling impact. Okay, and that's all from me. I'm and open for questions.
Thank you very much for the presentation, Bintang. So we're gonna have a 5 minutes Q&A section from the audience, and I see Monsieur Bourmeau from RTE have a question on the chat. Maybe you can unmute your microphone and ask directly the question if it's okay for you, Mr. Bourmeau.
Yes, thank you very much. Thank you very much for giving me the microphone. Can you hear me?
Yeah, perfect.
Yes, my question was about the CO2 first, about the CO2 emission. First, thank you very much for your very interesting presentation. I think it is quite comprehensive and it rings many bells with my personal experience. When accounting for CO2 emission, do you consider direct emissions due to mainly to fuel combustion, or do you take into account indirect life cycle emissions, like for instance, due to mining, manufacturing, installation, maintenance, or dismantling?
Yeah, well, the plan is to have the integrated assessment there, where we consider about also the land use impact of energy system. When we already consider the spatial dimension, we can also consider the impacts of this energy system, considered in the localities where the different energy supply system is being deployed. That also came up with an information on indirect land use emissions, and also in a energy network model, transportation of biomass also can be accounted for their emissions for the transporting part. So this information can be how we call it, can be evaluated when the model considers these resolutions as special temporal resolutions and the energy networks. Okay. I hope that answered the question.
Yes, thank you very much. Just an additional question. The way you integrate those environmental externalities are basically, if I understand you well, as constraints. Are you in favor of monetizing externalities, or do you prefer to stick with more obvious and obvious factors like what we get from life cycle analysis, which try not to mix distinct externalities and to keep separate, for instance, water pollution, human health, and biodiversity, to allow for a better understanding and the balance between those several impacts?
Okay, so correct me if I'm wrong. Is it about if we consider those aspects of the external energy system externalities to be considered in the model when we choose the best decision to make? Is endogenizing the impacts or the limits into the model? Well, to some extent, when the cost information for those externalities can be accepted for by means agreed upon, then it can be inputted as in the cost. But I think the more important part is in the more feasible way in doing this is considering it under the co-benefits analysis, because comparing it cost-wise can how we call it, to make the uncertain, because the cost information about these externalities cannot be compared face to energy system costing, because energy system costing is much more it's much more saturated. The energy technology is there, the cost is pretty much standardized, but then how about the cost of for example the impacts on land mining in the long term? we don't compare it with the cost of mitigating those. I mean, like to protect the, comparing it with protecting the land, because it has different impacts towards other externalities itself. For example, on how the localities can improve through ways of protecting the land, or actually mine the resources there. So an impact assessment could be very much more wisely happen compared to putting it into the model.
Thank you very much for
yeah. Thank you.
Yes, thank you very much for your very clear and comprehensive answer. Yes.
We have a time for a very quick question after we move very, very quick, if there is a quick question from the audience. Okay. If they're not, we will move to the next speaker, and we can ask a question
from Fabian.
Sorry.
If you want to receive it.
Sorry.
Fabian,
Sorry.
if you want to ask it.
Quick question. You're integrating this in the IASA model family?
Yes. And previously was working with Beware under the AFE, but now it's BNR. Yeah.
Okay, great.
Okay, perfect. So you can ask a question to Bintang on after the session, and I will move from the only one speaker on this morning who is not from TU Leona, which is Martin. Martin, we will present a paper about renewable energy targets under sector coupling. So Martin, you have 20 minutes and 5 to 10 minutes of Q&A question. And sorry about that, I will interrupt you maybe 5 minutes left for the presentation, if it's okay. The floor is yours.
Thank you. Good morning, everyone. Today I will be presenting a working paper supporting green gases with renewable energy policies, which I worked on with my supervisor, Leonardo Meeus. The title has since changed since I submitted the abstract, but very much the original research objective. So here's an outline for today's presentation, which is going to be listed at the bottom of each slide. So getting started, on the 2030 horizon, the EU aims to reduce greenhouse gas emissions by 55% and reach a 32% share of renewable energy sources. And these objectives also mirror specific climate and energy challenges. So there are multiple market failures to address which warrant intervention by policy. Two of which I highlight are the negative externalities associated with emissions and the positive externalities associated with knowledge spillovers or technology learning by doing. And so to these ends, the EU has existing policy tools such as the EU ETS and renewable energy policies such as support schemes. So some member states have implemented a sector-specific electricity targets where technologies like wind and solar were given direct support. And it's been argued by some stakeholders that low carbon and green gases are in a similar position today. They can play a key role in decarbonizing the gas sector, but today they're immature or not cost competitive enough. So given the experience with the electricity target, which is largely successful in deploying renewables, this has perhaps inspired some stakeholders to advocate for a gas target, wanting to replicate the same success. And the experience in electricity has also taught us that energy policy instruments may interact. So to future-proof renewable energy policy, this can also be anticipated. So in terms of what are green gases, they do not directly emit any CO2 of fossil origin. Hydrogen is an important molecule in industry and heavily relies on fossil-based energy. Two methods of hydrogen, green hydrogen production are water electrolysis using renewable electricity or thermochemical conversion of biomethane, for instance. And two methods of biomethane production are anaerobic digestion of organic matter or thermal gasification of biomass. And biomethane can be readily injected into the gas network and subsequently used in any demand segment. So I'll continue with the academic positioning. So as I said, their market failures related to CO2 emissions and knowledge spillovers provide an economic rationale for implementing a policy mix. And as summarized by Lehman and Gowell back then, one of the main concerns about electricity support schemes is interaction effects between instruments. So some criticisms such as CO2 emissions reductions in the electricity sector would simply be displaced to industry, but also that renewable electricity support schemes substitute a more expensive form of abatement for another. So, and the authors describe other market failures which also justify renewable energy support, which I do not detail here. And so Del Rio admits that policy mixes inherently lead to interactions between instruments, but suggests that this can be mitigated in the coordination or design. And the interaction effects between instruments, namely renewable energy and carbon markets, has been studied using numerical models, which is the approach that we take. So this brings us to the gap in the literature, formulated as two main research questions we try to answer. First, is a gas target and support schemes necessary to replicate the renewables deployment success of the electricity sector in the gas sector? We will study to what extent do existing policies support green gases. And second, are interaction effects between an electricity and gas target relevant in a multi-sector energy market setting? And if so, can we provide input for the design or implementation of a gas target? In terms of contribution, much of the debate has been about interaction effects centered around electricity sector and EU ETS, and we investigate interaction effects between renewable energy policies, so between an electricity and gas targets. And to investigate these research questions, we introduced a multi-sector equilibrium model with endogenized and policy-induced investment decisions. So this is not a pure electricity model. So formally, our modeling approach is a non-cooperative game consisting of agents participating across energy markets. We use the Nash equilibrium as a solution concept and reformulate it as a mixed complementarity problem. So I'll quickly describe the agents that we include. We have natural gas shippers and biomethane producers who supply the gas market. The demand for natural gas and biomethane is for further transformation for hydrogen production, by gas boilers for residential heating, or by gas generators for electricity generation. And then renewable generators also supply the electricity market, and the demand is for either aggregate consumption, powering heat pumps, or for power to hydrogen. And so these agents make investment in production or consumption decisions based on energy market prices, but also renewable energy certificate or emissions prices. And the role of the market operator agent is equivalently represented as market clearing conditions to obtain prices. So we introduce renewable energy policies which specify that a share of demand must be met by renewables. The associated dual variable is the feed-in premium then, which may be allocated to eligible technologies. So to meet a renewable electricity target, renewable generators and biomethane destined for electricity generation are supported. To meet a gas target, biomethane and green hydrogen are supported. And then we will also consider the case of a CO2 emissions market policy in which natural gas consumption, including for heat, is subject to a CO2 price. So here I will present our stylized approach with our main assumptions. So we assume perfect competition and that agents have complete information. It's a single shot model where investment and production decisions are taken simultaneously. It's an integrated market model, so we do not model network constraints. There are 4 representative days, which are considered to capture seasonal or daily characteristics. We take availability, renewable availability and demand data from a TSO ADIA and heat demand from a time series data set. We assume 1 representative technology for each agent and obtain the technology cost data from the DEA. We compute an equivalent annualized cost for each of them. And then we also assume that gas shippers and biogas producers have fixed variable costs. And lastly, for this type of model, we do not allocate the policy costs to the agents. So we consider 3 policies, as I mentioned, which drive the investment decisions of agents. The first 2 are closest to the status quo, while the third is a possible way forward. So the first policy is an electricity target. Given this policy, we run scenarios which change the ambition and investigate the solutions of each scenario. The second policy is a CO2 emissions market. So I will discuss the findings of these 2 policies first, policies and scenarios first, supported by figures. And later I will discuss the findings associated with the third policy, a dual electricity and gas target. So here's an overview of the findings in the same order. In the electricity targets scenarios, wind is the least cost resource renewable technology to meet the electricity target, and at an above 40% target, more wind capacity causes spillage or curtailment. And we illustrate with a 65% electricity target that biomethane and power to hydrogen are indirectly supported due to negative electricity prices. In the carbon emissions, in the carbon emissions market policy scenarios, a similar result is obtained when we take the CO2 target equivalent of the output from the 65% electricity target. Wind and heat pumps are the least cost means to make emissions reductions. But a more stringent emissions target increases wind capacity. This also causes spillage and electricity prices to go to zero in these periods. So the CO2 price would have to rise significantly, and eventually that would be enough to support green gases. So this figure depicts the result of one of the scenarios. So a 65% electricity target, as I mentioned. So over the 96 time periods, it illustrates the hourly generation in the shaded areas and demand via the stacked lines. In the top, so you can see substantial generation from wind, and its unavailability is complemented by natural gas generators. And as you can see in the last periods, there's substantial spillage from wind, and these cause negative prices, which results it reflects at which point the wind generator is willing to reduce its output because of the opportunity costs associated with foregone subsidies. So in turn, the wind generator earns no revenue in these periods, but the negative electricity prices incentivizes power to hydrogen, who is paid to consume. So next we'll look at the emissions target policy. So this figure depicts how energy supply and demand are met over an entire year in gigawatt hours and in each segment. So this scenario reflects a CO2 emissions target equivalent to the emissions that were resulting from the 65% electricity target we just saw. So in the electricity segment, we see that wind plays a major role, and in the heat segment, heat pumps meet nearly all of demand. So while wind is the logical outcome, the cost competitiveness of heat pumps improves against gas boilers as the CO2 price rises, and is a cost-effective way of displacing emissions. But as you can see, therefore, that an emissions policy largely supports mature or electricity-based technologies. And in the interest of time, I do not illustrate more stringent emissions targets, but if the CO2 price rises substantially as more spillage occurs, this can incentivize green gases. So as we can see, green gases are only indirectly supported by existing policies. So let's consider a dual electricity and gas target and investigate potential interaction effects. So the main findings here are that clear interactions exist. An electricity target can contribute to a gas target and vice versa. However, these interactions are substitutive, meaning progress in one may crowd out investment in the other. In other words, the final output of renewable energy in the electricity or gas sector depends on the coordination of the electricity and gas target ambitions. Additionally, the deployment of power to hydrogen appears to depend more on the electricity target than the gas target. Therefore, it's a bit unclear if a gas target is effective in supporting biomethane and power to hydrogen if defined in technology neutral terms. So first, I'll just demonstrate what I mean by interaction effects via three scenarios, illustrating renewable energy production over an entire year in gigawatt hours. So for each scenario, you can see a renewable energy's contribution to the electricity target on the left and to the gas target on the right. So one may expect that the combined effect of renewable energy policies be at least the sum of the parts, but that's not what we observe. So in scenario one, biomethane is the least cost resource to meet a gas target. In scenario two, wind is the least cost resource to meet a 25% electricity target. So you would expect scenario three to be the sum of these two individual targets, which is the total RES aim, but instead there's less. So scenario three combines both targets, and two substitutive interaction effects result. So for the gas substitutive effect, when biomethane is produced, part of the gas generation can then be counted as renewable. As a result, this counts towards the electricity target and crowds out wind investments. For the electricity substitutive effect, as you build out more wind, this displaces some gas generation. As a result, this reduces the total gas consumed, and thereby the total quantity of biomethane necessary to meet the gas target. So I'll not go into detail, but through the electricity and the gas target, this plays out and is somewhat cyclical. To evaluate the strength of these interaction effects, we look at the coordination of the targets. So taking some more scenarios. So in scenario 4 through 6, we doubled the ambition individually and together. So in comparing scenario 3 that we just saw to scenario 4, which doubles the electricity target ambition, wind increases by 165% and biomethane decreases by 27%, even though the gas target was unchanged. And in comparing scenario 3 to scenario 5, which doubles the gas target ambition, biomethane increases by 120% and wind decreases by 63%, even though the electricity target was unchanged. And then in comparing scenario 3 to scenario 6, which doubles both targets at the same time, wind more than doubles and biomethane only increases by 57%. Therefore, it appears that the electricity substitutive effect is stronger than the gas substitutive effect. And as we see here, the total RES is closer to the aim. So it is double of what was in this original scenario, but it appears that the more of the total renewable energy is provided by wind. And aside from these interaction effects, there are also clear interdependencies of the dual targets to highlight. So in the 25% electricity target and 10% gas target, but excluding heat pumps from the model in scenario 7, more biomethane is required as natural gas boilers are not substituted by heat pumps. Therefore, heat pumps help meet a gas target. Lastly, in the scenarios we've seen so far, biomethane is the least cost means of achieving a gas target, whereas power to hydrogen requires periods of spillage or curtailment to be cost competitive. And this is confirmed by scenario 8. So this kind of begs the question, if a gas target is deployed, whether the gas target is to deploy the least cost green gas, or is it to support a range of green gas technologies? So I now move to the conclusions, which are based on the 2 questions we tried to answer. First, can we replicate the success in deploying renewables in the electricity sector, also in the gas sector? So in theory, if immature and emerging green gas technologies are not directly supported by current policies and face technology related market failures, then the motivation for a gas target and support schemes could be justified. However, it's not clear which green gas will become most efficient in the long run. There's uncertainty about technology learning curves. So a policy could encourage a range of green gases which may not be achieved with a technology neutral gas target. The second question, are there potential interaction effects between dual electricity and gas targets, and what does this imply for the design or implementation of a gas target? We see that there's clear synergies are observed between the electricity target, which can contribute to meeting a gas target, and vice versa. However, this also means that there are substitutive interaction effects, which ultimately modify the final output of renewable energy in each sector. Therefore, to reach the desired goal of green gas deployment, these targets should be coordinated. That is the end of my presentation. Thank you for your time and attention. Happy to take any questions.
Thank you very much for this presentation, perfectly on time, even in advance. So thank you for that. So we have a 5 to 10 minutes question from the audience. You can ask on the chat or raise your hand if you have a question for Martin. Okay, Adam, go ahead.
Hey, Martin. Well, first of all, nice to see you. Great presentation. I don't know if you can hear me.
Yes.
Oh, yeah. So I was wondering if we, just to understand a bit from your opinion, from a perspective of, would considering storage and the network change any of these conclusions, have the potential of changing any of these conclusions? Especially on the part where you study the interaction between the gas and electricity targets?
Yeah, I think that's something that have to be looked at. I mean, for battery storage, we wanted to include it, but it's out of modeling limitations. So when you have renewable energy targets with battery storage and periods with spillage, so zero price periods, you have this unintended cycling of batteries. So it's something that can't really be included in the model. So that could maybe impact part of the findings of, or part of the cost competitiveness of power to gas. But I'm not really sure. Most of the scenarios that we looked at, for instance, do not really most of them don't cover that specific case. It's more of in low ambition scenarios and looking at the interaction effects between the two sectors. So I think that would still hold. And I did also think about, maybe you would want to do power to gas, so also do the methanation step and such. But yeah, that would also cover the more high scenarios. So at this point, I don't think, I think it's something that should be modeled, but it's I'm not sure if it would really change the conclusions that we have here.
Okay, great, thanks.
Thank you for the question.
Perfect. Okay, is there any question in the room? Okay, maybe I have a quick one, if it's okay. I'm not a specialist in mixed complementary equilibrium model, but do you have some cross elasticity estimation for price between natural gas and electricity price in the modelization, and how do you calibrate that, if you have one?
Indeed, maybe I didn't make that clear. So the demand here that we use is inelastic for each of the final demands. So we don't actually model the cross price elasticity.
Okay, thanks. And so is there any real data set with biogas you can compare your elasticity substitution that you obtain with the real world, or
That's a great question. I think that's it's really good feedback. Yeah, I think that's something I should definitely look at, actually, to possibly include. Yeah, I think that's also a sensitivity that we did run. I think we used one of the higher biomethane variable costs as an input. But yeah, at this point, without any additional support, it's not something that would come up. I think that's the idea, is that biomethane is subsidized to be cost competitive with natural gas, and that's essentially that. But thank you for the question.
No, you're welcome. I'm not sure, but I think in France we have 2 or 3 installations of biomethane. So maybe with NG or something like this, you can.
Yeah, and France is one of the few countries that does have like a. I mean, there's quite ambitious at the European level. You have the 40 gigawatt ambitions in Europe, which are just ambitions. But if you look at, there are some countries with actual binding targets. Like in France, they have a 10% biomethane target. So that's an example of countries that already have a gas target, which I didn't mention. So yeah, they plan on scaling up quite a bit in France.
Okay, thanks for your answer. Is there any question from the room? Yeah. Okay, Quentin, you can have the word if you want to unmute your microphone.
Hey, Martin, nice to see you, and great presentation. I was just wondering a simple thing. Do you intend to analyze some imperfect competition on one of the different markets that you are investigating?
Did you say imperfect competition? Can I get the question right? Quentin, did you say, or do I plan on including imperfect competition in the model?
Yeah, on one or 3 markets.
Yeah, I think with the model, that's something that can be easily included. It's just a question of whether, what the reason to motivating it. I guess you could have some imperfect competition in the shippers side of thing, which would raise the gas prices, which could in turn, increase the electricity market prices, because the gas generators are typically the marginal unit. I think that's something we could look into further. But in the past, when you think about other agents that could possibly be considered like imperfect, or when you reconsider the market structure, I'm not sure if biomethane or the green gases would really be considered like that, because you have power to hydrogen competing against other resources, and biomethane also more dependent on the subsidies than the actual cost structure.
As you have a 3 coupled market, if you have a market power from one actor in one single market, it must affect the outcome of the other market.
Yeah, I think that's yeah. Thank you for the feedback. Yeah, I think that's something that could also be future research, or at least maybe something that we could test out to see if that would impact the results to also include in this paper. Yeah.
Okay. Anyway, a great research. Congratulations, Martin.
Thank you, Quentin.
So there is another question from Mr. Bourmeau from RTE. You can unmute your micro and ask a question to Martin.
Yes, thank you very much. And thank you very much for the very interesting presentation. I have a question regarding the way you optimize, you perform the optimization. If I understood you well, you optimize in one go the installed capacity and the dispatch. How do you feel about the optimism of this optimization? I mean, in reality, market actors will face an installed capacity from competitors and then dispatch according to what exists. So a two-step approach could possibly yield quite different results. What are you feeling about that?
Yeah, I thank you for the question. I definitely could see how that could change the results. As I said, I mean, this is a greenfield model, and it is very stylized. So yeah, I think yeah, obviously some of the findings can be taken more cautiously. I think it needs to be maybe have a larger case, for example, or maybe even including this two-step optimization would also yield. But yeah, I don't know off the top of my head. I would have to try to see how that would change our results. How after listening to my presentation, do you think how do you think it would change my results that would motivate doing this type of two-step optimization?
My personal feeling is that we could see lower efficiency of the cross-sectoral coupling, basically. Of course, it's just a feeling, not a scientific conclusion. But I would be interested.
Yeah, well, I'll look at investigating that.
Yes.
Thank you.
Thank you very much.
I think we can move to the next speaker. So thank you, Martin, for your presentation and for the great session, Q&A questions that you have. So Frida, the next speaker is Frida Revheim, sorry for my pronunciation, from TU Wien, and she's going to present a paper which is called Sector Coupling of a Local Energy System, Influence of the Local Dependent Parameter.
Yeah, thank you very much.
You have 20 minutes, and I will interrupt you 5 minutes left.
Okay, perfect.
Thank you.
Yeah, so hello everyone. My name is Frida Revheim. Before I start, I would just like to apologize for any background noise. Unfortunately, there is a construction in my building today, so I hope it will not be too disturbing. Yeah, so today I will present a work that I'm doing together with my colleagues Daniela Schwabeneder and Georg Lettner from the Energy Economics Group at TU Wien. The paper is about sector coupling of a local energy system, and we want to evaluate the impact of location-dependent parameters on such a system. So the paper is still in progress. So the results that I'm presenting here today are the preliminary results that we have so far. Yeah, so I will start by introducing some of the motivation behind the work. Before I then move on to the methodology and the preliminary results. And then I will finish off with some ideas for further work. So energy sector coupling could be an economically viable solution in order to ensure continued implementation and operation of distributed renewable energy sources. So in other words, it could help us reach the greenhouse gas emission targets, and additionally, by utilizing sector coupling concepts, we could also be able to reduce curtailment. However, to which degree these benefits will occur or how present they will be will probably depend a lot on location-specific parameters such as electricity generation by renewable energy sources, the local energy demands, and also which options of alternative fuels that are available. So that's why we wanted to do a comparative analysis of a sector-coupled local energy system, where we then evaluate the impact of such location-specific parameters on the systems, both operation and also the profitability. So in the paper, we have some KPIs that we want to investigate in order to evaluate the performance of the sector-coupled system. So we want to look at the profitability, so how profitable the system is under the given assumptions. We also want to look at how the different technologies are utilized within the system. Another important KPI is how well the system is able to reduce greenhouse gas emissions. And we also investigate how well the system is able to be self-reliant in terms of meeting local energy demands with renewable energy that's produced within the system boundaries. We are also looking into how much energy that is being purchased externally, so from the market. And finally, we also want to look at the curtailment that's happening. So in order to investigate all of this, we have developed an optimization model of a sector-coupled system in Julia. So far, it's a purely operational model. It doesn't consider any investment costs. The objective of the model is to maximize the profit while meeting the local energy demands and, of course, also following the technical constraints at all times. So the objective function is shown here, and we have revenues related to selling electricity to the electricity market, selling hydrogen to the gas market, and selling hydrogen to industry or mobility. And the costs are related to buying electricity from the electricity market, either to cover the local electricity demand or for feeding into the heat pump. And there are also some costs related to buying heat from an alternative heat source to cover the local heat demand, and buying natural gas from the gas market to cover the local gas demand. So here is a figure which represents the system that we are investigating. So it includes both power to heat and power to gas technology through the implementation of the heat pump and the electrolyzer. So the wind farm generates electricity that can either be used to cover the local electricity demand. It can be sold to the electricity market, it can be curtailed, or it can be fed into the heat pump or into the electrolyzer. The electrolyzer then produces hydrogen that can be used to cover the local gas demand, or it can be sold to the gas market or to the industry sector. There are also some waste heat produced in this electrolysis process, and that waste heat is then used to cover the local heat demand. And the remaining heat demand is then covered by heat from the heat pump and heat from an alternative heat source. So we then defined 3 separate use cases. So one Austrian use case, one Norwegian use case, and one Spanish use case. And each of these use cases had or have individual location-dependent parameters. So the parameters that we chose to investigate or have as input were then the electricity generation from the wind farm, the local electricity, heat, and gas demand, the electricity prices, the gas prices, and the price for alternatively produced heat. We also considered the type of alternative heat source available and the corresponding emission. And another parameter that we had was the electricity mix of the use case. So as I said, we have defined 3 separate use cases: Austria, Norway, and Spain. The Austrian use case is assumed for the Neusiedl am See region, with 4,290 households. We assumed a wind farm that has an installed capacity of 32 megawatts. And based on data from Eurostat, we found that the majority of the heat demand is covered by natural gas, but also district heating and electricity are important sources to cover the local heat demand. For the Norwegian use case, it's based on the municipality of Åfjord with 1,961 households considered. The wind farm here is assumed to have an installed capacity of 57.5 megawatt. And the majority of the Norwegian heat demand is covered by electricity. Yeah, so for the Norwegian use case, we didn't consider any local gas demand. The Spanish use case is made up of several smaller municipalities, summing up to approximately 1,000 households. The wind farm that we considered here was assumed to have a capacity of 31.5 megawatts. For the Spanish use case, we didn't consider any district heating demand, and the majority of the local heat demand is met with gas, but also electricity is an important source. So for each use case, we investigated 3 different scenarios. So scenario 1, which can be considered the baseline scenario, we didn't consider any additional technologies implemented. We only have the wind farm present. So that means that the heat demand is fully covered by heat bought from the alternative heat source, and the local gas demand is met with natural gas bought from the gas market. The electricity demand in this scenario is met either by electricity generated by the wind farm or electricity bought from the market. So in this scenario, we really don't consider any sector coupling at all. In the second scenario, we've included a heat pump, and we assume that households that normally rely on gas for heating would now connect with a district heating grid and be supplied with heat from the heat pump instead. So the heat pump is then scaled to be able to meet this increased local heating demand. In scenario 3, we implement both a heat pump and an electrolyzer. So we now assume that households that rely on district heating will be provided with heat from the heat pump, and if necessary, heat from the alternative heat source. And we also assume that households that rely on natural gas will be able to be supplied with hydrogen from the electrolyzer as well. So the heat pump and the electrolyzer are then scaled based on the local heat demand and the local gas demand. And this basically means that for the Norwegian use case, there is no electrolyzer because we didn't assume a local gas demand. And for the Spanish use case, there is no heat pump because we assumed no local district heating demand. Yeah, so moving on to the preliminary results. First, we can have a look at the economic results for the 3 use cases. So for the Austrian use case, we see that the third scenario, with both an electrolyzer and a heat pump implemented, is the most profitable one. And this is mainly due to the revenue from selling hydrogen from the electrolyzer to the industry, which then significantly influences the profitability of the system, even if it means that less electricity is available for covering the electricity demand. From the second scenario, we see that by introducing a heat pump, the costs related to covering the local heat demand can be reduced. Yeah, so an electrolyzer is not implemented in the Norwegian use case under the given assumptions. So that means that we don't see this significant rise of revenue in scenario 3. Actually, scenario 2 and 3 are identical under the current assumptions of no local gas demand. But what we do see is that sector coupling through the implementation of a heat pump leads to a slight increase of the total profit also in this use case. Yeah, so for the Spanish use case, we have a similar situation. We see that the implementation of a heat pump in scenario 2 leads to lower costs related to covering the heat demand, which then again results in a higher total profit. Yeah, so regarding how the implemented technology is utilized in the different scenarios, we here have an example of how the system is operating in the Austrian use case for scenario 3. So that's a scenario where both a heat pump and an electrolyzer are implemented. So we see that a lot of the generated electricity is being fed into the electrolyzer, and this is due to the revenue that the system obtains from selling hydrogen. And the majority of the remaining electricity is then either sold to the electricity market, or it's being used to cover the electricity demand. Another interesting observation is that the gas demand is fully covered by gas that is bought from the gas market, because all of the produced hydrogen is sold instead of being used to cover the local gas demand. We have also had a look at how the heat demand that is usually covered by district heating and gas in the 3 use cases is affected when we introduce these sector coupling technologies. So in the Austrian use case, we have a heat pump and an electrolyzer implemented. However, because the hydrogen is so lucrative to sell directly, we still rely on natural gas bought from the gas grid in order to meet the demand. We also see that because the electrolyzer is used so heavily, the waste heat that is produced is able to cover quite a significant share of the heat demand. In the Spanish use case, the entire heat demand is covered by natural gas bought from the gas grid. But for the Norwegian use case, the situation is different, as we don't assume a local gas demand and therefore don't have an electrolyzer implemented. So the heat pump is here used to covering the majority of the heat demand, and the remaining share is then covered by heat that is bought from an alternative heat source. Yeah, so looking at the potential for greenhouse gas emission reduction in the different use cases, we see that significant reductions are possible. So the way that we calculated this was that we compared the emissions of the original energy sources, so natural gas, biopellets, and the electricity mix of the use case, with the emissions of the new energy sources that the sector coupled system offers. So from this, we then found the reduction potential. So the potential would then depend on the size of the implemented technologies, as well as the electricity mix and the alternative fuel sources. And also the size of the system that we are investigating will have something to say here. And we see that the Austrian use case, which has the most households, is also the one with the most reduction potential. Yeah, so what we see is that by utilizing locally generated electricity and heat from the heat pump, we are able to reduce emissions. On the other hand, the implementation of an electrolyzer does not really affect the emission reduction potential because all the hydrogen is sold to the industry. Yeah, so for the renewable energy self-reliance, we are considering how much of the local demands that are covered by local renewable sources. So the top figure here shows the local electricity demand, and we see that the majority of the local electricity demand is covered by electricity generated by the wind farm in all scenarios and all use cases. The exception is perhaps the Austrian scenario 3, where only around 50% of the electricity is met by locally generated electricity. And this is again a result of the electrolyzer being implemented and the high revenues that come from selling the hydrogen. If we look at the degree of energy self-reliance related to covering the heat demand, we see that it's significantly affected when we implement the heat pump. Also here we see that the Austrian scenario 3 is a special case where then the majority of the locally produced heat is actually waste heat that is being produced in the electrolysis process. Yeah, so under the current assumption, sorry?
Frida, sorry, 4 minutes left.
Okay, I think I will manage. Anyways, so under the current assumptions that we are using, where the gas demand is totally dependent on gas bought from the gas grid, we see that the degree of self-reliance when it comes to covering the gas demand is really not affected by the technologies that are implemented. Yeah, so we've also had a look at the external energy purchase in the different use cases. So first of all, there's obviously a clear correlation with how self-reliant the use cases and scenarios are. As I mentioned, natural gas is necessary in order to cover the gas demand in all scenarios where we are considering a gas demand. And we also see that the amount of electricity bought from the gas grid and the amount of heat bought from the alternative heat source depend on the size of the technologies implemented. So for example, in the third Austrian scenario, more electricity needs to be bought from the grid in order to cover the electricity demand, because so much of the generated electricity is already being fed into the electrolyzer. Okay, so the last KPI that we have investigated is the potential for curtailment reduction. So the Austrian use case was the only use case where we originally had curtailment due to negative electricity prices. And if we compare the curtailment in scenario 2 and in scenario 3 with the curtailment that's happening in the baseline scenario, we see that by utilizing sector coupling concepts, we are actually able to really reduce the curtailment that's happening within the system. Okay, so from our analysis and from our preliminary results, we see that by utilizing sector coupling concepts, we have the potential to reduce greenhouse gas emissions, to increase the degree of energy self-reliance, and also to reduce curtailment. But of course, how big or how important these benefits of sector coupling are will depend on local conditions. So some ideas for further work could then be to focus more on determining the optimal system topology based on the local conditions, and also to, for example, investigate how local policies and regulations could impact the system operation. Okay, so just at the very end, I would like to mention that this work is done in collaboration with the Thermoflex project. And yeah, thank you very much.
Thank you very much for the presentation, Frida. So we're gonna have 5 to 10 minutes Q&A question. So is there any question from the audience? You can write on the chat or raise your hand.
There is a question from Nikolaus. He raised his hand. If you want, you can take the mic, Nikolaus. Perfect.
Hi, Frida. Thank you a lot for the interesting presentation. I was just wondering, maybe I missed it, but what was the hydrogen price you were assuming?
We were assuming a price of 170 euro per megawatt hour for the hydrogen in all 3 use cases. This is based on research that we've done to what the industry is willing to pay for green hydrogen.
All right, thank you.
Okay, is there any other question? If it's not, I have 2 quick questions, if it's okay.
Sure. Okay.
So do you think about including some uncertainty about the wind electricity production?
Sorry, can you repeat the question?
Sorry. Do you consider to use some uncertainty about your wind electricity production? Which I mean, like, okay, sometimes the wind farm can generate this amount of electricity and this time of this amount. The kind of to provide some stress test of your energy local system, which I mean, if there is no wind or if there is a wind.
Yeah, so far we are not doing this, but this is definitely an interesting approach. Yeah, so it will. I think it's something to work, so that it's worth looking into.
Thanks. And my other quick question is, do you think about test your local modeling in France, where most of the electricity is based on power generation, and the peak demand is managed from gas demand, from gas power generation. So I don't know how this kind of market distribution for electricity in France could impact your modelization.
Yeah, thank you. That's also a very interesting point. So far, we only have so a Northern European country, Middle European country, and Southern European country, but would definitely be interesting to include other countries with other local parameters. So yeah.
Thank you very much.
Thank you
for your presentation and for your answers.
Okay. So I think I'm back.
Perfect. So last chance to ask a question to Frida, and after we will move to the next speaker. Okay, well, we will move to the next speaker. So the third paper today, it will be presented by Fabian Schipfer, if I pronounce okay. And the paper is called Techno-Economic Catalogue for System Flexibilization. So Fabian, are you here? Yeah, perfect. We see your screen. So you have 20 minutes. I will try to interrupt you 5 minutes left, and the floor is yours.
Thank you very much. Give me a second. Okay, so now you see the presentation, right?
Yeah, perfect.
Without the notes and stuff, right?
Yeah, it's perfect.
Okay, thank you very much. Okay, thank you for the kind introduction, and thank you, dear panel and audience, also to listen. I see this is quite some session, which could be an energy economics group internal around, but I also see that some of you already presented quite some good stuff about bioenergy too, which is more the topic in my presentation here. I'm presenting on behalf of the IAEA Bioenergy TCP Task 44 on bioenergy flexibilization. And the bioenergy TCP from the IAEA combines international expertise specifically on different technologies, such as bioenergy combustion, gasification, liquefaction. But there are also some tasks, like the Task 44, which focus more on the systemic and strategic analysis of the energy system and the role of bioenergy. In the Task 44, we specifically looked at the added value of flexible bioenergy, with one result being a techno-economic catalogue for system integration to inform especially scenario modelers and modeling forums in our vicinity of our scientific groups. I think I can skip the introduction why flexibilization is important, and especially Bintang also presented quite some good points on variable renewable electricity production and the need for flexibilization. But it's also especially good to look at this 6 phases of system integration of the IAEA, which paints a picture of how also in your scenarios of your system models, you will encounter different types of flexibilization needs. So there are phases when renewable electricity will not really have quite some contribution to the energy system. You will have almost no flexibilization needs, but at some point you will have to invest in additional flexibilization. This depends on different countries. In Austria, for example, we have a lot of pumped hydropower storage, and the investment comes a bit later, or investment needs comes a bit later than in other countries. And then as more variables you integrate in your system, as more flexibilization needs you will have, and in the end you will even have flexibilization needs for seasonal or even interannual surpluses of variables. One of the advantages of our technology collaboration program of the IAEA Bioenergy is that we have experts sitting in different countries who can give their opinion about their countries, how variables integration looks like right now in their country. What we see is that most countries are already in phase 3 and seem to invest in flexibilization. So this is also a limited number of countries we have here, but that's the countries where we have expertise in. And at the point of writing, considerable shares of bioenergy are also integrated in the energy systems of these countries, especially when you compare it to the shares right now in photovoltaic and wind. And at the same time, these country and flexible bioenergy experts report that the main barrier for bioenergy to unfold is, or for bioenergy to unfold its flexibility potential, is found in the regulations and the political framework and the economics in these countries. You can see this in the 2 lines up here. Give me 1 second. I can turn on my. Hope to turn on my power laser pointer. There we go. So these lines here, you see that's the main barriers which were identified in these countries. So we can summarize in this first motivational slide that first of all, it's not, or it should be clear by now that we will need all sustainable flexibility options to boost further integration of variables or intermittence. But the regulatory and economic barriers are quite high for flexible bioenergy options. Thus, we assume that the understanding of potential benefits must be apparently quite low, which leads us ultimately to the question, what are the potential benefits of flexible bioenergy and how can they be valorized? To start, first of all, we have to answer the question, what's the definition of flexible bioenergy? The current consensus in our group is that it's defined as a bioenergy system that can provide multiple services and benefits to the energy system under varying operating conditions and or loads. There are clearly also other prevailing and advanced alternatives, such as grid expansion, demand response management, and other options you already mentioned in the presentations before. But bioenergy gives us a multiple options how to further advance in this field. And to make a quick first look or first picture on the options we identified here, and some of these options have already been also presented in the presentations before. I want to especially highlight here in this overall picture 3 main aspects of this multiple options of flexible bioenergy. First, this topic is a supply chain topic. Supply chain was also before mentioned by Bintang. It's something which goes through the entire bioenergy research. Supply chain in the sense of from the forest until the, for example, heating device in a residential building or tank of a fuel car. So the flexibility can be found in different parts of this biomass to end use chain. For example, in the feedstocks part, but also in applications in energy carriers, but also the intermediates. Second, we have many different options, as we already mentioned, which are again interlinked throughout the supply chains. And third, some of these options are already commercially available. You see here the different TRL, the technological readiness level of the different technologies. This is an estimate coming from the experts which contributed to this report. We see especially some technologies like combustion of dry biomass in residential heating being quite high TRL commercialized, but also especially biogas production and also biomethane grid injection are widely used in widely used in Germany or also in Austria and other countries. And also flexibilization from biogas, for example. You have in Germany the biogas flexibility premium for flexible electricity production from biogas. So these technologies are already there. But where we see specifically further demand for technological development is when we go to hydrogen integration into this system. For these options to be able to unfold their flexibility potential in reality, first of all, we have to unfold their flexibility potential theoretically in the integrated assessment models and other energy system models efforts. After a year of work, we can say that we are still in the beginning of constructing a full-fledged techno-economic catalogue, which could support this work. To account, first of all, for feedstock flexibility, we will have to include parameters such as seasonal occurrence, spatial availability, but also the properties of the main product when we talk about residues, or the negative or also positive impact on ecosystem services. They have to be considered for the feedstock flexibility part, so the beginning of the supply chain I'm talking about. For the bioenergy carriers, the intermediaries, such as wood pellets or biochemicals, we draw on an own field of research, but also on flexibility from short and longer term electricity storage. The energy and carbon density and biostability will be specifically decisive for the cost calculations here. Further self-ignition risks and also existing infrastructure, for example, biomethane gas grid injection options are important here. And then we come to flexibility in the most narrow definition, only in the electricity system itself. There it will mainly have to be discussed based on the already discussed and accepted parameters such as ramp rate, capacity, duration, and other frequency constraints. But then, and also very interesting, finally, the biomethane or the wood pellets can be used for a set of different services, such as heat, but power also, but also plastics production, for example, through via gasification, and also, as already mentioned today, for negative emissions, or even nutrients production. These options open up a completely new discussion of product flexibility, especially when we talk about the circular bioeconomy. For all supply chain links, economic, environmental, and socioeconomic parameters are central in this catalog. Now I want to spend some time on the conclusions of this work before pitching again the new updated flexibility definition we come to. First, again, we will need all available sustainable flexibility options to enable further integration of the variable renewable energies. But the regulatory and economic barriers are at the moment high for flexible bioenergy options specifically. This is mainly because the potential benefits of flexible bioenergy and how to valorize them is unclear. What makes this work even more complex, but also much more exciting and promising, is that bioenergy flexibilization potentials address different dimensions throughout the supply chain, going way beyond intraday grid balancing. But also for all these potentials, looking only on the component or firm level, we mainly find added costs if there is no support in place. The added value, we assume, is only provided via the overall system integration. And for the system level assessment, our preliminary catalog has to be extended to consider, first of all, long-term flexibility, contributing to the power sector, mainly of the intermediaries and bioenergy carriers, which can be stored over longer periods of time. On the next level, also the contribution to the overall energy system beyond electricity, especially residential heat and industrial heat. And finally, also the broader bioeconomy and its goals, thus including, first of all, on the one hand, sustainable feedstock flexibility, and on the other side of the chain, the product flexibility and other services of the bioeconomy. Finally, and after this work, we define flexibility from different perspectives, from the process or component level perspective and from the system perspective. And we extend flexibility with different dimensions, including temporal and spatial flexibility, feedstock flexibility, operational flexibility, flexibility in the use of bioenergy and end products. We are looking forward to publish the final report soon on our homepage. Thank you very much for your attention, and I'm looking forward to your feedback and questions.
Thank you very much,
Fabian. You can also send me questions if you have questions afterwards per email.
Thank you very much for the presentation. So just check if you want to ask a question to Fabian, you can raise your hand or write on the chat.
Just a quick reminder, Fabian, if you could upload also your presentation to the dashboard as a presenter, I think. Thank you.
Okay, maybe I have a quick extension question. So you mentioned that what is your implication about the policy implication of your work? Which I mean, do you think you need a kind of regularization that manage the firm to be able to see the all different substitution and flexibilizations you can have on a grid or something like this, and provide some subsidies from the government to manage at the whole level and not only at the firm level?
So we discovered more or less in our discussions the problem that we don't know yet how to valorize it and how to especially put it into formulas which address these different dimensions of flexibility. So the first step, and that's what our next triennium is going to be about, which starts next year, we will address the question how to integrate it into our system models, and thus find out actually how to valorize it. And from there we will only have the conclusions how to address it in the policy landscape. So we are more on theoretical level here and quite far away from really integrating it. I mean, what is clear for now, and what we also address in our policy discussions, it will be needed to address the energy system as a whole, and actually also extend it to the economic metabolism of all our products going in and out, and input and output of our economy. This is a short, I mean, but this is clear to all of us, right? We have to extend our scope, and it has to be integrated holistically. But how we are going to do it is going to depend on how much we can price in, how much we can put into really economic value, and that means also the environmental dimensions and social dimensions, how much of this can be priced in. Second part is, where do we need our regulations, so incentives, but also where do we need clear rules and standards, how to run stuff, and targets, where we want to end up in next years. And the third thing is, which is partly overlooked actually, how do we make the culture change for people to demand, to want actually the more sustainable solutions. But this is a very general answer, I know, and this is also a general answer for.
Oh, it was a general question, so okay. It's a general answer. So is there any other question from the audience for Fabian? Okay. So thank you very much for your great presentation, Fabian. Maybe we let 1 or 2 minutes left for last question, but I'm not sure you have another question. Sorry about that. So, and just keeping on the generalities, what is your dream natural experiment case? If you like, I don't know, land in Vienna or a city or something like this, to try to manage your theoretical implication.
Can you repeat this?
Yeah, sorry. I mean, my question is so. If you have to implement your theoretical insight on natural experiment, I mean, do you prefer a city level or country level, or what do you think? That's it's easy to manage for you at the city level, or maybe it's the same for everybody.
So the focus of the work is very much on bioenergy. So the city level is an interesting use case, but it's impossible to neglect the importance of the non-city level of the country, right? So you have to get a biomass from somewhere, and actually the big implications with bioenergy are also to have the added value in supply regions of the country. So that's where you also create the jobs and the businesses. So you can actually you can never focus only on the city level here. And then on the European level, it's very interesting because we have circular bioeconomy strategies going on the European level. So this is mostly we talk in the European level, and we talk also we have close ties to the US, which have a different perspective on the circular bioeconomy, on how we approach the sustainability issue in general, more technology focus and business level focus. And we will have to find out how we come together here.
Okay.
And then still, this is only, okay, I'm already going too far, right? But then you have to see it on the global level where we have the different depths, so to say, regarding CO2 budgets. So you can, and then there's also international trade, especially of intermediaries.
Okay.
Maybe this answers your question.
Yeah, thank you very much for your answer and your great insight. So I think I will close the session for this morning. Thank you very much for all the speakers and all the attendees. It was very interesting and great presentation. So enjoy the rest of your conference, and I hope to see you in another session. Thank you very much. Bye.
Thank you.
Thank you, everyone.
Thank you.